Okay, it's 1 o'clock, so we are going to go ahead and get started. Thank you everyone for joining us today. My name is Delaney Duran, and I'm a PhD student at the University of Delaware and the president of the American Shore and Beach Preservation Association Students and New Professionals Chapter, or ASBPA SNP. We're really excited to have you here today for our Engineering with Nature Reef Systems for Coastal Protection webinar. And we've got some really cool speakers lined up, and I'll tell you more about them in a little bit. First, I just wanted to set some general ground rules for today. So, all attendees are not able to unmute themselves, but if you have questions for us, please feel free to drop them in the chat. Myself and Tyler Jacobs will be monitoring the chat, and we'll make sure to address any issues. If you do put anything in the chat, please make sure that it is respectful. And additionally, we have federal employees here today, so we want to make sure that our questions are respectful and appropriate for the presentations that they're giving. And I think with that, I'll go into my introductions. So we are joined by Dr. Amanda Tridinger today, and she will be giving us an awesome overview of engineering with nature and an introduction to set the stage for our other speakers, including Dr. Kurt Storlazzi with USGS, who's going to be talking about coral reef applications, and then Katie Simi, who is a PhD student at the University of Miami. And finally, Cassie Everett, who is a research civil engineer at the Army Corps. Cassie isn't able to join us today, so I'm filling in for her. So please go easy on me later in this talk. And Amanda, if you're ready to go, I'll have you kick things off. And I also just wanted to add a personal note. I have Amanda's Wave textbook with me, earmarked from all of her stuff, and I use it all the time. So thanks, Amanda. Personally, very excited to have you here today. And I stopped sharing, so you should be good to go. Okay, can
Awesome.
you?
Yeah,
Perfect.
no problem. Thank you. Thanks, Delaney. Yeah, so excited to be here. Love ASBPA, love SNP. So thank you for the opportunity. All right, so my name is Amanda Tridinger. I'm a research hydraulic engineer here at ERDIC's Coastal Hydraulic Lab. My background's in physical oceanographic engineering and mostly numerical modeling, but I'm also the deputy program manager for the Engineering with Nature program. So today I'll be talking about that program, what we're covering, and how it kind of works. Before we jump in, I just wanted to give some resources. If while I'm talking you want to scan the web, you can look at this QR code that's on screen and go to our website. We have a really great search bar, so you can search any keywords and find what you're looking for pretty quickly. And then in the bottom right corner, there's the Network for Engineering with Nature's website as well, where you'll get some of our network materials. That said, Engineering with Nature, or EWN, is one of our research programs here at ERDIC. And our goal with the program is to intentionally align our engineering practices with environmental processes. So we want to make sure that the projects, the infrastructure we're putting in the ground, it has multiple benefits. It's using what is happening locally to build up and create more resilience within the project itself. And we want to make sure that we're also looking kind of at the macro scale. So we're not just looking 10 years into the future, but 50 years into the future, and providing a project that will naturally align itself with the shoreline, provide those benefits, and be more resilient in its life cycle. Just to hit that ethos before we move on, I'm sure everybody on the call loves the coastal zone, but I call it the resilience zone. This is where the land meets the water, and here are just some of the benefits and the things that we find at the coastal zone, why it matters. This is where we find coastal habitat, ecosystem, beach dune. It's where we get recreation. It's where humans can see estuaries, see the water. We have urban communities along the coastal area. I believe at this point we are a little over 40% of our population lives within a coastal zone. And by 2050, it's projected for that to go up to 60%. This is where we have a lot of transportation. We have ports. This is our access to commerce, imports, exports. It's very important. Unfortunately, the coastal zone has a lot of high level risk. So we have storm surge, erosion threats. We've also witnessed coastal squeeze. So as that population becomes bigger along the coastline, the area for us to rebound against those natural hazards becomes smaller. So we've been seeing a lot of channel shoaling and just disequilibrium in our sediment budget. So our sinks are higher than our sources. And we've seen intensified natural hazards. So this is why it matters. This is why we need to come up with infrastructure solutions that are resilient and why we're turning to natural infrastructure to do that. Some coastal system considerations are listed here. And in the bottom right, I have a really nice chart that just shows, based on the scale of the problem you're assessing, the risk, the hazard, versus the scale of the area you have versus the scale of your event, your wave action, your surge. There are certain kind of this Venn diagram of what infrastructure or natural infrastructure solutions you have. And reefs fit nicely into the temporal scale of the higher wave energy, the morphology on the coast, matching the scale that you have at the coastline. You may have noticed I use the word natural infrastructure. So before we dive into the EWN program in detail, I want to talk about natural infrastructure as a continuum. So natural-based solutions, natural nature-based features are all terms we've passed around. A reef is an NNBF, but I think it is important for us to look at the bigger system, the watershed scale, and create systems-based engineering where that reef feeds into what's happening on the shoreline, what's happening in your navigation channel, and just looking at that natural infrastructure scale solution. So I'm going to use the word natural infrastructure to mean multiple lines of defense within this presentation, but natural-based solutions, NNBF, very interchangeable, especially when we're talking about constructed oyster reefs and how they fit into that natural infrastructure. All right. Enough of the intro. Here's the EWN program. So as I mentioned, the goal is to align engineering practices within the Corps, within the nation, internationally, with our findings on how the environment, the ecosystem, geomorphology, vegetation, hydrodynamics, how they're working already. We do this through collaboration, research, demonstration projects, pilot projects, implementation, and then communication. And I'm going to use the following time to give examples of each. So first off, collaborate. We want to make sure that what we're doing isn't done alone. We have the right people at the table. ERDIC itself has 7 different laboratories, all representing different disciplines. And as we create this natural infrastructure solution, it's important to include those multiple disciplines. We have complex problems we're solving. We need to make sure we have complex solutions with the right subject matter experts solving them. So one way we do this is we have the Network for Engineering with Nature. This is a highly collaborative group. We get together monthly. Actually, today we have a monthly meeting where we'll be learning from Stantec what they're up to. But we have 32 plus partners within the network that are all looking at natural infrastructure from their perspectives. This includes 11 universities. We have industry. We have big business, we have small business, we have other federal agencies, a lot of folks just interested in doing natural infrastructure together and collaborating on projects and providing kind of sweat equity resources. Internally, we have these proving grounds. So if you're familiar with USACE, we have basically these districts that are located at each different watershed breakup throughout the continental US. And a few of those districts have said, I want to implement the latest and greatest EWN, make me a proving ground. So as we have research ongoing, we kind of have this iterative process with those proving grounds where they implement that research. They tell us what works, what doesn't. And before our research tasks end, we can kind of realign the ship so that on the ground practitioners can use the research and the tools we're creating. Along the way, we learned that permitting and policy were kind of more of the hurdles that EWN was facing through implementation. So we started to get proving ground divisions, which are the people that sit above the districts as a whole and are able to oversee projects, kind of use the vertical chain of command to smooth things out and implement quicker. So we work a lot with our districts and those divisions. Research, we're a research program. We have many different research tasks within EWN. We've been kind of an initiative within the Corps for over a decade, but in the last 5 to 8 years, we've been federally funded to support research, and that's, of course, a huge part of our portfolio now. And this portfolio includes a lot of different research types. We have case studies, we have field studies, we are doing, tools, remote sensing methods, LiDAR, beneficial use research. We do a lot of numerical modeling, R&D, as well as physical modeling. And the portfolio also looks a lot at the coast, but has branched out. We're looking at fluvial and arid regions, cold regions. We have a very expansive, kind of diverse area of interest, as well as inclusive. We've been inclusive in like multiple types of disasters and looking at water quality, quantity, not just shoreline erosion and storm surge. So I point that out because it's, like I said, you want to have all the right people at the table. You also need to look at that watershed scale we're seeing. Like scaling up your natural infrastructure is really important. And that research being so diverse helps us do that. An example of some of the research we have, I'm going to talk about the numerical modeling toolkit. This is a graphic user interface that's been developed to augment natural-based features into existing numerical models rapidly, so that we can see how these features perform in the models we use every day. And there is a reef function that you can basically drop a shapefile in, tell the GUI this is a reef, and then it'll semi-automatically mesh your reef into your numerical model. Next up, we have a lot of physical modeling projects. Delaney's probably going to talk about one of them. Here's a study that we did back in 2016, I believe, where we looked at different dune geometries in our wave flume, as well as how to include below and above ground biomass to represent the dune. In this study, we used a prototype to represent above and below biomass to see at what threshold do you get no more return on benefit for adding biomass below the dune or above it. And we used Courier fiber to represent it. Fast forward to 2022, Lee Langley started a research task to say, okay, that's what it looked like with what we represented as dune biomass. How is an actual natural dune performing? So we teamed up with University of Florida, as well as the Environmental Lab and Coastal Hydraulic Lab. And we had a field study test, not only looking at how dunes were performing in the field hydrodynamically, but how they were creating ecosystem benefit for creating nutrient addition, and how we could plant dunes in a way that they would grow quicker, be more mature faster, just best management practices for creating a stronger dune more rapidly. And we did these site experiments. We analyzed the site data, and then in 2024 they developed this dune sampler where we cut out a dune and brought it into the flume, and we're able to run those similar tests to the 2016 one to see how a natural dune would perform. And so all of this data is just to show, and these examples of the research really rapidly shared, it's just to show like we have numerical modeling, we have physical modeling, we have case studies, and they all kind of communicate to each other to fill the gaps in knowledge and build out best management practices for implementing natural infrastructure. Okay, so next up, implementation. It's great to do state-of-the-art research, but it's not going anywhere if we don't see how this research performs in the field. So we have these proving grounds that said, hey, we're going to work with you. And because of that, we have these pilot projects where we're able to test out and implement our research. And we have many different case studies that are available. You can see on the website. But all of this led to the development of the international guidelines on the use of natural nature-based features for flood risk management, which is this was published a few years ago. We have 4 separate parts with overreaching topics like how to start a project, to how to create monitoring adaptive management for that project, assess alternatives, communicate benefits, expectations. And then in coastal applications, there is a chapter for reefs specifically that if you go to the website, you can see it's a 1,000-page document. You can get a 100-page blurb just on how to implement reefs. But this was a very highly, like I said, it was international. We had over 84 different authors and a lot of people got involved. So this was kind of the first step tool on how to implement NNBF. As of this last year, we've kicked off a more specific publication series on engineering guidance for different natural nature-based features. So the International Guidelines book kind of talks about how to start a project, what to consider, where the EWN engineering guidance documents are looking at how to implement the performance, the risk analysis, the factors of safety, the engineering performance part. So we have since published the floodplain benching manual and engineering practice guide for oyster reefs, which feels important for this specific webinar. We are in the process of publishing that right now. It's in our ITL, our IT department. So stay tuned. Our engineering practice guide for oyster reefs should be coming out within the month. Oh, and then lastly, we kind of implemented, based on that engineering guidance, based on those international guidelines, we said, per these districts that are interested in implementing, what does it mean for you to take these tools and create projects at your locations? Because not everybody's features are going to be the same. Their forcings are going to be different based on what coast you're on. Your availability of species for natural infrastructure is going to vary based on region. Where that natural infrastructure is going to do well, that's also going to change. So we've created these kind of how-to books for each district so that they can implement based on what is available to them in their region. Okay, lastly, communication. EWN is really big on making sure everything we learn gets out to the public, to various audiences. We do that by creating different types of communication per audience. So an example of one is we have our EWN Atlas series, which is a coffee table book full of example projects. This is great for talking to stakeholders and saying, I know it seems crazy, but we're going to put concrete at this depth and oysters will come. This is a great way of just saying, hey, these projects look great and they do well and they have been doing well. We also have a podcast. If you don't like to read, you can listen and you can just see what episodes interest you and see what we're up to. We also have the typical kind of technical reports, journal publications, and what's expected from research, all available at the engineeringwithnature.org website. We also, lastly, for communication, we have a monthly webinar series every third Thursday. The next one's next Thursday. We're going to be presenting on the EWN Compass, which is a GIS tool for implementing natural-based features in your area. You can sign up by going to the noon.org or going to engineeringwithnature.org and searching Noon Knowledge Webinar Series. It's a great way to just see who's doing what and get 45 minutes of some subject matter expert telling you what they're up to and how to implement. So yeah, that's EWN in a nutshell. Again, here's the QR code. And I think at this time, I can take any questions.
Thanks, Amanda. We're going to have about 5 minutes of questions, so feel free to put those in the chat to either myself or Tyler Jacobs. And Amanda, I'm going to get you started with one of the questions are registered and submitted. And I feel like you covered some of these. One question was about monitoring. So are there any recommendations or in the permitting process, anything that you specify for how long your proving ground project should be monitored?
This seems to be case by case. I think the language says long-term monitoring, which is pretty vague. So that needs to be kind of it needs to be socialized with whatever organization did your like NEPA, whatever did your permitting evaluations. You socialize what long term means. I've seen a year, I've seen 3 years. If you can get 3 years, I think that's best for everyone. Um, but yeah, to answer your question, I think a year is what I've seen the most often be for reefs for monitoring. That said, I've seen some really cool projects partner with other organizations with and build out a monitoring adaptive management plan that says we will do this for a year. Then at that point, we're going to turn it over to Fish and Wildlife or a different partner or a grad student. And we can, there's certain like documents where you can share the monitoring equipment and do this in kind sort of thing so that you can have monitoring happen longer. And I think longer is better, especially as we want to justify more projects. We can point to these other ones. So it's not just for like the performance of your project, it's for the betterment of the community of practice.
Thank you. This next question kind of goes into that, but someone asked about how long are the design lives of the different EWN projects? I feel like this is case specific, but do you have like a goal design life?
Um, yeah, it is case specific. When we look at, I think 50 years has been pretty typical for us to look at future alternative designs. We have been doing some engineering with nature for military application with installations, and for those we end up looking at like 100 years into the future because they can be a lot more conservative with their assessments, and they have to. Like it's more like hold the line versus move the line kind of conversations. Yeah.
Cool, thank you. I feel like 50 years makes sense. The next question we got was about support. Does EWN work with international groups or international firms?
Yeah, we've had a lot of partnerships, as you saw with the NNBF guidelines, with international groups. We work with the World Bank, a lot with Rick Waterstaat in the Netherlands. Um, we've currently been kicking off some projects with Brazil, with a group in Brazil. And then personally, yeah, we've worked a lot OCONUS with again with the military groups we work with. Um, so yeah, we love working internationally. And I just got back from the EGU, the European Geoscience Union, where EWN did a lot of networking and was well received. So we love international partnering.
Awesome. Thank you. Another question we got ahead of time was about, and I feel like you mentioned permitting, but what are the biggest challenges that you have found with implementing these nature-based features in like the real world, like outside of the proving grounds?
Definitely permitting has been the biggest issue always. We've done so many surveys with practitioners inside USACE, outside. Permitting is always the problem. Um, one of the one of the solutions I've seen to that is before you even get to designing, you start talking to the permitters about what you're going to do. So before you get to requesting a permit, you say, hey, what are you going to look at when I fill this out? So that they're not surprised by it and you can kind of get past that second step of response. Also, windows have been issues. Like, yeah, there's just like a lot of different windows depending on where you're permitting, like turtle windows and nesting times, depending on what you're doing, that kind of delays a project. And then lastly, if precedent, like finding, and that's why monitoring is so important. If you can find precedent where this project has been done somewhere else successfully within your region, that can either progress the permit quickly, or if you can't find it, be a problem. So being able to find precedent is huge.
Cool, thank you. I feel like those are awesome answers and maybe not things as engineers and for me as a grad student we always think about. So thank you.
Yeah.
I'm gonna close your case specific question and answer session now, and then we're gonna move on to our next speaker. Dr. Kurt Storlazzi from USGS. Kurt, feel free to share your slides.
Thank you. Oh, Jesus. Well, thank you for having me here today and presenting a bunch of work me and my numerous co-conspirators have done over the past about 5 to 10 years. Hope I'm going to show you how we've taken some basic and applied research and really have changed, federal, state, local policy and the private sector. And to do that, we needed a, consortium of folks from, research through policy. So just to be clear, the U.S. has over 3,100 kilometers of coral reef line coastlines, which is longer than the U.S. Gulf or West Coast. However, we know due to global stressors, reefs are bleaching, or land or local stressors like pollution and overfishing is really causing a lot of these reefs to degrade. And what we've seen is over the past several decades, U.S. coral reefs have lost over almost 3 feet of elevation and also roughness. And thus now they're less effective at dissipating wave energy and reducing flooding. So one of the things we're looking at is to both restore degraded reefs or enhance those as a nature-based solution to provide coastal protection and other ecosystem functions. I'm showing a picture of a restored coral reef here. Just want to be clear, like the reef is not just the live little coral polyps, but is the large geologic structure. And so we think of reef restoration as not just the corals, but outplanting them on a carbonate structure, limestone, concrete, to make up for that loss of mass. So over the past better part of a decade, we've combined some oceanographic, coastal engineering, ecologic, geospatial, social, and economic models to assess the coastal protection value of coral reefs. So basically, we understand the hazard, we understand the role of that ecosystem in reducing that hazards, and then most importantly, the consequences of that. What changes policy is when you talk about dollars and lives, and we could translate it to that. I'll show you how. So here we show, and again, along that 3,100 kilometers of shoreline, we've done basically this process at 10 meters resolution. So here we show flooding for the 100-year floodplain with current reefs. We know for a building in the 100-year flood hazard zone, the probability of flooded during a 30-year period is about 26%. So then what we do is we numerically restore the reefs. We make them taller, make them more hydrodynamically rough. Then we rerun the flooding models, and so now the flood zone's in green. So the area you're seeing in blue now is the area that be protected by coastal flooding. And with reef restoration, the probability of flooded once during a 30-year period decreases by 20% in Florida and Puerto Rico. What we can do is we cross-match this with U.S. Census, so we can know the number of people protected. We can also cross-match it with HAZAS data, which is buildings and property values to understand the property protected. Now, we do this for a number of different return storm intervals, in this case, the 10, 50, 100, 500 year. And we do this because the way that the insurance industry, FEMA, the Corps, and others calculate and analyze risk reduction benefits is you basically do a magnitude of impact by the probability of occurrence. In this case, you'll see the lines are showing red is the current reefs, blue is the restored reef, so we're lowering the risk. That gray area in between is the benefit. And basically, you take the integral of that, you can get an annualized value. So we did this again at 10 meters resolution along all 3,100 kilometers of coastline. We show that coral reefs protect over 18,000 people per year, about over $2.5 billion annually in terms of coastal protection. So one of the things is, again, but let's talk about, these reefs have been degraded. What happens if we enhance them? So assuming a coral reef restoration and 30-year maintenance cost is about $3 million per kilometer, equally split between initial deployment and then return maintenance of the things, outplanting as species die, have bleaching. And so here's showing a map of off Florida and Puerto Rico. Benefit cost ratios, when they get into the blues, those are greater than 1, and so they have a positive return on investment. whether if you need an immediate return on investment or your financial model such that it can be paid out over 30 years at a 7% discount rate, that goes up to 20%. FEMA or the federal government just reduced this discount rate from 7% to 3.3%. So all these numbers that probably double. And remember, or pointing out the highest return on investment generally occurs where communities, infrastructure, and economic activity are located. So why does that matter? Well, in all these tools usually used to fund gray infrastructure, such as seawalls and breakwaters, then can be used to fund green infrastructure, such things as pre-disaster mitigation grants, restoration funds, special purpose task districts, catastrophe bonds, resilience bonds, all those. And why does that matter? Because the National Institute of Building Sciences showed that every dollar spent in mitigation saves $4 in averted damage for tropical storms. So, okay, so great, we could do this. Well, that's great science, but let's see how we've moved it forward. So one of the things we did is we kept sure that these data worked within the federal system. So here you see basically these flood data in FEMA's flood assessment structure tool. What that did is it allowed the states and territories to use this data to apply for FEMA grants, like the BRIC program, which is over $2 billion a year, the Hazard Mitigation Grant Program. The Commonwealth of Puerto Rico used these data and got basically the first successful Hazard Mitigation Grant Program award to restore 7 kilometers of coral reefs off the capital and the international airport. And that process is now moving forward. The Department of Defense used these data to justify $70 million programs to make hybrid coral reefs grow faster and be more resilient to cost effectively protect tropical coastal military bases from storm-driven flooding. I mean, this is DARPA. The people brought you the internet, stealth technology, mRNA vaccines. Nice investment by them. On the on the public sector, or on the private, should say private sector, Lloyd's of London, Swiss Re, Munich Re, they're all, because we followed their guidelines and did these assessments, they're basically saying that, gosh, they're starting to think about how, hey, coastal hotel, you protect your coral reef, we're going to reduce your rates. Conversely, if you damage those reefs, we might increase your rates. This has gone so far that the Nature Conservancy, using some of these results, worked with the Bank of America, and they got the first ever insurance policy for coral reefs in the US. So they're insuring those reefs that if a storm happens, so here's the 2024 policy update. Basically, if hurricanes or tropical cyclones get within these different zones, they'll pay out because they know those reefs will be damaged by those storms. The payout will fund folks to go out and rehabilitate those reefs to bring back their protective capability. So where do we stand now is what are the next steps? I'm glad Katie's here. I'm showing some sea highs, but really, we're really at the nascent stages of this actually being implemented. So we need to get these test bed structures deployed, outplanted with corals, and make measurements of their performance to calibrate and validate models. Once we have those models, then basically we need to have those calibrated models to look at them, determine their performance at test levels, so that we understand that they can provide the protection function. And really, what the designers want to do is maximize energy dissipation, thus reduce the wave during flooding or erosion hazards, while minimizing the volume of material and thus the cost. This is actually University of Hawaii's base structures for the DARPA field experiment. And just to show you that again, we're looking at turbulent kinetic energy dissipation as you're moving through these porous structures. Just to let you know, this little simulation here, 28,000 core hours. So this is non-trivial kind of work versus what Amanda was showing some great flume studies, but this is to take it up to field scale. So that was my presentation, and any questions? Thank you.
Thank you, Kurt. As we did with Amanda, if you have questions for Kurt, please drop them in the chat to either myself or Tyler. And Kurt, I'm going to get you kicked off with some questions that were submitted ahead of time. And I think this is a perfect question with your simulations. What key parameters are used for numerical modeling of coral reefs?
Well, one of the biggest ones we have is hydrodynamic roughness. And the more you dive into that topic, I think the more complex it gets because it's a function of, your incident wave parameters and water levels. But one of the things we're trying to really tackle now is at what point does bathymetry become roughness? And that's really kind of fascinating. And because what we want to do is you want to have a more hydrodynamically rough feature. Obviously, showing you with those porous concrete structures that causes a lot of more turbulence, basically reduces energy, and that provides the coastal protection. So you need morphology, you need roughness. Those are the two key parameters. Obviously, we're getting much better at forcing, obviously dynamically downscaling either like ERA 5 hindcast or like now we're running CMIP 6 GCMs to get future waves and things like that.
I have a follow-up question to that. Are there any data that you typically use that are more difficult to get than others?
The data is more difficult. Well, see, I don't want to say beaches are easy, but you have typically kind of like your normal Dean profile. Coral reefs vary incredibly. Some of them are 15 kilometers wide, some of them are 100 meters wide, and the roughness is with them. And so, at least in the U.S. and the territories and commonwealths, we have LIDAR. A lot of our other folks that we work with. Some other countries we work with, we don't have that data. And so just having that bathymetry, I mean, obviously, the bathymetry is the biggest control in wave propagation and coastal total water levels. But then again, also at the finer scales, the roughness of that, like what's the coral cover? So,
We got some questions in the chat as you were talking. Someone connected your work back to, I think, what Amanda was showing with the Army Corps, but have you used any USACE cost benefit tools in this work?
We have not. Again, we've been primarily working with FEMA here because they've got, again, the hazard mitigation program is about $2.3 billion a year. The building resistant infrastructure communities is also over $2 billion a year. And those are open things that we've worked with states and the territories, well, commonwealths, to help have them design successful FEMA programs. Like I said, we got 38.6 million for Puerto Rico. We got about 7.7 million for just more advanced BCA benefit cost analyses and initial design for Florida. And I think we got 1.2 million for, again, more stakeholder engagement, more design for Hawaii so that then they can go out then put in a larger 40, 50, $60 million for installation. But yes, we've not done that with USACE yet. Doesn't mean we're not looking to. Amanda, happy to.
Our next question came from Joan Pope, and she asked if your storm models look specifically at waves and wave energy, or are storm surge elevations also included, specifically with the flood risk projections?
Yeah, so we're doing both waves and water levels. Let me be clear here. Just this is an important point for this group is that storm surges, remember, you need a big continental shelf. So the only place that storm surge is a really big factor is in Hawaii. I mean, sorry, it's in Florida. Most of the other places, well, all the rest of the states and territories, storm surges, even for, Cat 5 tropical cyclones, is on the order of, a few decimeters, where wave-driven water levels are on the order of meters. So, but yes, in our studies, we did do both waves and wind-driven water levels.
Yoshi asked a really cool question. He asked about your insurance policy for coral reefs, and
Not mine.
well,
Bank of
the
America's.
the one you mentioned, and he asked how would different Pacific territories start that process of getting their own reef insured?
Um, Well, so what had happened? Well, I don't know how exactly the process. I can tell you how it happened in Hawaii. So the Nature Conservancy took the results our larger group developed. They kind of wrote a white paper on that. Then they had conversations with Bank of America, and I'm sorry, I'm a coastal geologist, Ocean. I don't know everything about it, ensuring nature, but it worked. So, and just let me be clear, the Nature Conservancy first did this in the Mesoamerican Reef, basically just south of Cancun. So that's where that was first designed. But now it's, been acceptable to U.S. Federal, state, territorial governments. So clearly there is a process. I'm sorry, I can't speak to the intricacies of that.
Thank you. I appreciate you doing your best with that one. This is actually a really interesting question too from Tracy Schrock. They asked if there has been any research on how the continued degradation of coral reefs may affect the coastal protection benefits.
Ooh, there was a paper out in AGU's Earth Future by Storlazzi et al. Just a few months ago on we modeled basically future projection. My colleague Kim Yates, who just retired out of the USGS, modeled how different, I think 12 or 13 different habitat categories on the Florida Reef Tract are projected to degrade over the next or by the end of the century. So we ran our current flood models, then we ran it with the future degraded, and now, obviously, it goes further inland, and we could quantify the dollars and lives in there. So yes, check out AGU's Earth Future 2026. We've done that, and that number for the state of Florida is on the order of $1 billion annually if they let that reef degrade. And I'll say this is the chief resilience officer. Well, when we showed that restoration would provide protection on the order of $670 million a year, Florida's chief resilience officer, that passed through the state Senate, and that's why, or the state government, that's why they're now putting $20 million a year towards their own state funds towards coral reef restoration, primarily for the hazard risk reduction aspect of it. So, yes, degradation will increase risk, restoration can decrease risk. It's the state and local people's decisions on what to do with that information.
I have one more technical question, and this might come up into play later as well, but has there been any sort of local erosion of sediments around, I guess, restored coral reefs or some of like the newer reef technologies?
Well, so we are actually, again, in such nascent stages of all this. We've gotten the first test beds. Katie's going to show one of those got deployed off North Miami Beach Park, but we're really just putting these first ones out. And so their stability, them causing scour and erosion, the engineers that are designing these are taking those factors into account. Um, but yes, I mean, obviously, if you're putting something off soft sediment, it will, cause local scour. Um, but hopefully you've designed it such that it will not, be negatively infected or cause negative impacts. So,
We got to follow up on that. Somebody asked if the degradation in modeling, or sorry, is that degradation considered in modeling parameters like roughness?
yeah, basically that's how we do it. We do it by two things, height and roughness. So the bathymetric elevation and hydrodynamic roughness. And that's a great that's a scientific topic. Again, I think that we're very early stages trying to understand that is like how species, you think about like, Amanda was talking, I mean, we're doing a lot of modeling, like these are all subgrid scale processes. Usually your coastal engineering model, if you're modeling, you know, 3 kilometers or 5 kilometers. We're not doing an open foam like I showed that last video. I mean, that thing was 13 meters wide and that cost us 28,000 core hours. We're going to do something on the order of kilometers. Those are coastal engineering models at the scale of meters, grid cell sizes. And so stuff like roughness is a subgrid scale parameter, and us understanding how to parameterize that based on like, hey, we can go out and structure from motion or high resolution sonar and get really high resolution bathymetry and into the size of corals and stuff, but how that turns into a wave friction factor, a current friction factor, there still has to be a lot of work done on that. So all you graduate students out there, good topics.
Thank you, Kurt. I appreciate your time. You got a wide breadth of questions. I appreciate your effort in answering them. At this time, we're going to transition to Katie. And Katie, if you can hear me or not, I'm adding in the chat. Feel free to go ahead and share your slides. And yeah, Katie is a PhD candidate at the University of Miami, and she will be discussing her research on sea hives today.
Okay. Uh, can everyone hear me, first of all? It's good? Okay, thanks. So thank you for having me. My name is Katie. I'm a fourth-year PhD student, as was mentioned before, at the University of Miami on the Marine Science campus. And I will be talking about the Sea Hive, which is a multi-purpose nature-based solution. So more about me and specifically about this presentation. I really focus on the physical modeling aspect, and I'll be talking more about the capabilities of the SUSTAIN lab that I work in and more about how we can model things like the sea hive in the lab as opposed to the coral or financial aspects of breakwaters and things like that, because I don't really want to touch something that I don't know enough about. But I have attended one ASBPA conference and two FSBPA, so very happy to be here. So the Alfred C. Glassell Sustain facility, we have two tanks. One is Sustain, hence the name, which is the biggest wind wave tank in the world. And then the smaller one is Assist, which is harder to see in the bottom. But they are both capable of filling up with seawater and freshwater, and we can run up to scaled Category 5 hurricanes within these tanks. So this helps with a lot of different fields and within physical oceanography, but to look at the open ocean as well as things that are happening on the coast, which is important for what we're talking about today. So here are a couple of images of things that we've done within the past year. The two spray looking images at the top, we have a sprinkler system to help us look at sea spray, and then the one on the right is just to look at hurricane style winds. And we are focusing on nature-based solutions right now. So there's the sea hive at the bottom and then a mangrove, scaled mangrove forest at the top. And yes, so specifically we focus on investigating, well, today, the protective coastal concepts and wave energy reduction strategies and evaluating new materials and commercial products for coastal, atmospheric, and land environments. So these videos are pretty cool. Here is the smaller tank. And this experiment was looking at the dissipation of the effect of mangroves on wave dissipation. And then here we have a cool video of stress over a house using Category 5 type winds. And then lastly is the most important one in my opinion, which is the sea hives. And this is a channel that was made and we are looking at the dissipation of the waves over the top of the sea hive structures. So specifically, the sea hives will be addressing two major concerns, which would be coastal erosion around Florida, and I will only focus on what we know about the Florida coast. And so the University of Miami is in Miami-Dade County, which exists in the top 10 coastal communities most frequently hit by hurricanes. And so trying to reduce coastal erosion and flooding is really important for us at the University of Miami. And so this picture I took not even half a mile from our campus. And this is a series of jetties that had been put out there a long time ago. And you can see that there is more sand and sediment on one side and not on the other. And so it's very locally an issue that we deal with on a daily basis. And Florida has a ton of hotspots of erosion probability occurrence and active erosion that we're seeing on a daily basis. So The Sea Hive is definitely a new type of breakwater. There's a ton of other traditional breakwaters that are used very often, but sometimes have adverse effects, including trapping of sedimentation and inhibiting sediment transport, as well as um, causing other issues. And so this image is actually from an FSBPA, the top with the huge wave going over the seawall. And that is in St. Augustine, and that is showing the adverse effects of a wave going over the top of the seawall. And I think that was pretty damaged. And I think at the conference, they talked about trying to rebuild that. And then the picture on the left is something I took again, where it's showing a damage study. And so these issues are showing us that we need to start kind of considering other options for preventing coastal erosion and things like that. And so submerged breakwaters have been around for a long time, but we are all trying to optimize them on a daily basis. And they have a lot of other advantages, including controlling sedimentation offshore and economic and physical advantages. And this will include vegetation and juvenile coral outplanting, protection for plant and animal life, and increased biodiversity and improved cost efficiency. So again, as has been mentioned before, there's a decline in the coral reefs around Florida due to bleaching events and increased sea surface temperature. And it is known that coral reefs help with mitigating the wave energy that occurs before it hits the coast. And it's important to keep them around and to try to rebuild these areas to make sure that they are naturally helping with the dissipation of wave energy. And so we are trying to look at how we can help them and the corals, but also how we could mimic that with the breakwaters that we are trying to implement in the water. So a lot of artificial reefs have been implemented around Florida. Florida actually has one of the most active artificial reef programs. And these images were taken from the Florida Fish and Wildlife Conservation Commission. And you can see that they have a lot of different shapes, but they are all trying to do the same thing, which would be to establish a habitat as well as monitor or to inhibit the wave energy that's going to hit the coast. And so specifically, we'll be talking about the Sea Hive. And this is the Sea Hives that Kurt was talking about earlier that are in North Miami Beach. And this was right at the beginning of the deployment. So what is the Sea Hive? The Sea Hive is a modular hexagonal perforated structure that is intended to be used as an artificial reef foundation that can be stacked and arranged in various configurations. And so modular meaning that you can take not necessarily one, but we can stack them in different ways depending on the site-specific needs. And that is important because oftentimes traditional breakwaters, submerged breakwaters have a rigid structure that is typically one trapezoidal shape or something along those lines that can't really be modified depending on what the desire is for. And so the Sea Hives are offering an improved blueprint for submerged breakwaters, reducing performance inconsistencies while offering flexibility and structural arrangement, like I was mentioning. So at the top, we see some sensors on top of it to look at the stress around the structure. And then these are also part of the pilot installation that occurred at the bottom right. And then the bottom left was another pilot installation that was backing a seawall. So like I'm saying, they can be arranged differently depending on what is necessary. So the sites with the Sea Hive deployments that I'm mentioning today, and there is one perspective, but that might not be the case anymore. The one in North Miami Beach is this top right, and this the first image is at the initial deployment, and then the 3 years later is that one image over there. So you can see that there's fish and corals and a lot of an ecosystem built up on top of that. And then on the left is the pilot installation in Wahoo Bay. And so there there is a live camera, but it hasn't been working, so I don't think you can see that right now. But that is one of the cool things about these installations is that you can basically monitor what's going on if we, try to put a camera in there, people who are interested in what the sea hives are and how they're changing over time. We can put cameras in and also like just have the community also be interested in that as well. So specifically, what I have been doing with the sea hives is focusing on how we can model and test the sea hives in the lab. And so these are all various different scaled models and designs of the sea hives over the years. And so we have the ones on the top right, which are very, very tiny. And I think that was a 1 to 20 scale. And then some others that were 1 to 10 and 1 to 8.5 scale. And so I think one of my questions from earlier was how do we make sure that this is accurately modeling the concrete structures that I was showing before in the lab. And the geometric aspect of it is scaled properly. The ratio of the perforations to the length and the void space is all scaled appropriately, which we can do with AutoCAD and because we have a 3D printer and things like that. But the material itself is the only thing that's really could be an inconsistency there because concrete is really hard to, we can't really 3D print that small of concrete without a lot of rebar and other support that would inhibit the shape of the structure and what we're trying to accomplish here. And so the middle picture, you can see that there are staghorn skeletons on there. And that was another project. So it was implementing the shape of a type of sea hive and then also putting the corals on top to see how they are impacting the wave over the reef. So specifically, I was looking at, this was a project I did over the year. I was looking at the change in porosity. If we change the porosity of the sea hive configuration, how does that affect the wave energy transformation over the structure? And so because these are skeletal structures and they have porosity, eventually, and even when they're put into the water immediately, you're going to have sediment buildup and other things that will inhibit the flow through the structure. And so that is known and expected, but we want to get an idea of how that actually, how much the porosity would aid in the dissipation of the wave. And so that's what I looked at, and I still have some data to analyze. So this is kind of just an outline of what I've done, but it's a very interesting time to be in the academic community with things like nature-based engineering and exploring different types of submerged breakwaters that are perforated and have these void spaces because everyone's trying to figure out the best way to incorporate the porosity into these general equations that we've had, for many, many years within coastal engineering. And so if you consider the fact that we have void space within a configuration, and since these sea hives can be stacked, it's void space times however many you're going to have in that configuration. There is another term that we have to consider of the porosity when we are thinking about depth limited breaking over the structure. And so I've been looking into that and trying to run experiments. Experiments take a long time, and things like a wave flume. We are constantly building things up and taking them down, and sensors that we have to put up and things like that. So it is something that will take a while to come up with empirically, but it's important because the sea hives are so unique to kind of get an idea and quantify how that, if we can quantify the flow over the structure and how the porosity is influencing that. And so the configuration I looked at specifically, I do want to mention, is 74.8% porous. And that is far higher than traditional submerged breakwaters like a rubble mound. in that case. So they are definitely more porous than things like that, and that is also important. Okay, so future testing, and this is what I'm about to be doing within the next week or so, is running another experiment in that smaller tank in Assist, and I will be using a different scaled sea hive structure, but I am trying to break down all of the components of the wave energy transformation over the structure. So due to the depth limited breaking, the drag force over the structure, and the reflection, and how all of that is contributing to the total wave energy flux. And so that will take a long time, probably the whole summer, but I'm excited to start doing that again. And we are going to also make the structures completely non-porous, so we can look at the difference between that, because before I was using things like tape to cover up the perforations. And then we are also going to be comparing it to the typical trapezoidal shape that you see normally. We also just acquired a new PIV system, a particle image velocimetry system, that will allow us to look at the turbulent flow. So that's also very exciting. That will give us a lot of insight into what's happening inside and around the structure. And I do have a picture of our cameras there for the PIV system. And then this is a video of what the laser looks like, that as it shines through the water, we can illuminate the particles and how they flow. So that will be pretty exciting to use over the sea hives and within. So thank you for your time. The main contact would be my advisor, Dr. Brian House. So his email is there. And I hope I introduced the sea hives okay.
Thank you, Katie. Can you still not hear me?
No, I can hear you better now, actually.
Oh, perfect. Okay, well, thank you very much. Great talk, and you definitely provided a great overview, and it sounds like you're gonna have a really cool data set already and then coming online this summer. As we've been doing throughout this process, if you have questions for Katie, feel free to drop them in the chat, and then I'll read them out loud and Katie can answer them. Katie, to get you started, do you have any idea of how the results from your physical modeling studies compared to the pilot studies in the field in terms of like recruitment, or I guess not recruitment, but like wave attenuation and transmission?
So everything is scaled, like I was saying, also the wave conditions and the water depth in the lab. And so the depth, the submerged depth of the pilot installation is quite a big depth to scale in the tank. So that has been something that we've been trying to look into, and that things like modeling will be helpful for, because we can only fill to a meter in the big tank and then 45 centimeters in the small tank. And you would have to make very, very small structures to be able to mimic what I think is 2 meters in North Miami Beach submerged depth. So the conditions are scaled and similar. That's just taken from the wave information study buoys. And then, a linear wave theory is applied, and we can look at those conditions. But the depth is harder to model. But yeah.
We had another question asking if you're going to consider any lift forces in your studies.
I don't think so. The drag coefficient that the equation, that awful equation that I put into there, it really just incorporates the porosity over the structure and the shape. We've talked about making the structure more rough, and that versus the acrylic that we're using, but that is something that I need to look more into to address that question properly, but not lift, as far as I know.
Okay. One other question before we move on. Do you have any instrumentation on your pilot studies, like out in the field? Are you measuring forces or waves or anything like that?
So that was done. So the North Miami Beach, they were deployed in June 2023, and those or they weren't deployed. The sensors were deployed out there during that time, and with Kurt and USGS actually. And so there was some wave gauges and vectors that were put out there, and he probably would know more about that than me. But as far as I know, that is going to happen again with the other installation that just occurred around the same area. And so there's this big move to this coming year to start installing more sensors, which will probably, the data will probably be collected far after I've graduated. But that will be more wave gauges and pressure sensors and things like that to look at the flow around the structure, and hopefully some more offshore and inshore so we can actually get the full span of the energy transformation that's occurring around those. Yeah.
Cool, thank you, Katie. We're gonna go ahead and close Katie's session of the Q&A. Katie, you're more than welcome to address any of the questions in the chat that have rolled in. And then I'm gonna be our last speaker for today. We were supposed to have an awesome speaker, Cassie Everett from the Army Corps, but she had something come up, so I'll be presenting some of my PhD research on oyster-based living shorelines, and this is a preview of my talk for ICCE next week. So please go easy on me, and if you have any questions, this is a good time for me to address them. And I'm going to try to share my slides. Okay. Is everyone seeing the PowerPoint view or the...
We're seeing the software, not your PowerPoint.
Okay, how about now?
Correct.
Okay, I just can't see any of you, but that's all right. Okay, hi again, everyone. My name is Delaney, and I am a PhD candidate at the University of Delaware studying coastal engineering with Dr. Jack Palayo. I will be discussing our experiment of wave attenuation by a concrete-based oyster mat. And first, I just wanted to set the stage for oyster-based living shorelines. So these oyster-based living shorelines are designed to mimic natural oyster reefs, which provide a range of ecosystem services, including carbon sequestration, water filtration, habitat creation, and importantly for engineers, shoreline protection. They exist on a spectrum of natural or green to more man-made or gray, as Kurt had discussed earlier for coral reefs. And the natural oyster-based living shorelines generally have an emphasis on oyster shells or recycled oyster shells, and their shapes more closely resemble natural oyster reefs. As we move along that spectrum, we get more man-made elements, and the picture on the right shows a reef ball, which is entirely constructed of concrete. I also wanted to describe some terminology because there's a lot of variables in this presentation, and I want to make sure we're all on the same page. So if we consider an idealized environment with a flat bed represented by that gray rectangle and the still water line, the difference between the two is called the depth, or H. And then if we look at our oyster-based shoreline represented by this trapezoid, it has a crest width B and a structure height HC. And the difference between the water depth and that structure height is referred to as freeboard. We can also think of these variables as relative water depth, which is the ratio between the water depth and the structure height, and is kind of a proxy for submergence. In our system, if we add waves, we have our incident wave height, and then that wave has an associated peak wavelength and peak wave period. We can then describe our structure in terms of its relative crest height, or the ratio of its freeboard to that incident wave, as well as relative crest width, which is the ratio of our crest width of the structure to the incident wave or the peak wave wavelength. Our incident wave is going to interact with our structure, and some of that wave energy is going to be transmitted. So we'll have a transmitted wave height, and we can describe the amount of transmission in terms of a wave transmission coefficient, which is the ratio of the transmitted wave height to our incident wave height. And then some of that wave height off the structure is going to get reflected back. And so we describe that with a wave reflection coefficient Kr, which is the ratio of the reflected wave height to the incident wave height. For successful oyster-based living shorelines, we need to carefully balance ecology and engineering requirements. And this means for oysters, typically those found on the East Coast or the Gulf Coast, the eastern oyster, they require a 50% inundation duration, so they need to be submerged for about 50% of the tidal cycle in order to cycle nutrients, cycle waste, grow, and survive. And Morris et al. Did this really cool study on oyster-based living shorelines that range from more natural to man-made, and they broke their results out into greater or less than that 50% inundation duration. If we focus on the greater than 50%, the pink highlighted area, which is where the oyster reefs are the most happy, we notice two things. First, we have a big range in transmission coefficients from 0, which is almost entirely full wave attenuation, to almost 2, which suggests that the wave heights more than doubled when they interacted with the structure. And then secondly, we notice a wide range in freeboards. So in this case, freeboards are around 0.5, positive 0.5 to negative 2, indicating that the structures within that greater than 50% range are either low crested or submerged. This brings us to our oyster mat, and these two pictures show an example of about a 1/4 meter squared oyster mat. They're constructed generally by zip tying oyster shells to some sort of flexible base material like the biodegradable BEAS element on the left or a plastic netting on the right. These studies of these oyster mats have shown that they have strong recruitment potential in the field, and they're generally used as an ecological restoration tool. However, as engineers, we noticed that the oyster shells are allowed to kind of move around freely, and they're not sticking in a vertical orientation, which resembles natural oyster reefs. So we considered if we have a more fixed base like concrete, we can stick our oyster shells in and they're more rigid, and then they more naturally mimic the shape of a natural oyster reef. Wave attenuation studies on oyster mats are fairly limited, so the goal of this experiment was to determine the effectiveness of concrete-based oyster mats at attenuating wave energy under a range of wave conditions and submergence ranges. To answer this question, we conducted a physical modeling experiment in the Army Corps of Engineers 3-meter wave flume in Vicksburg, Mississippi. This wave flume is about 60 meters long and equipped with a piston-type wave maker. The waves propagate from the left-hand side of this image over a 1/44 slope into a flat testing area and then end in a dissipative beach. We had a total of 17 wave gauges in this experiment. They were capacitance-type wave gauges and were calibrated prior to installation in the wave flume. We had 2 5-gauge reflection arrays in this flume, one offshore near the wave paddle and one onshore near the beach, and the remaining 7 wave gauges were spaced in a flat testing area, with wave gauge 8 and wave gauge 7 bordering our oyster substrate, represented in green. We had 2 oyster substrates in this experiment. First was our concrete-based oyster mat. We were very lucky to get to build this oyster mat directly in the flume. So we poured concrete into a wooden form and then hand-placed oyster shells at a random orientation but with a vertical orientation, and then allowed the mat to cure for 4.5 days. This resulted in a 3-meter longshore, 2-meter cross-shore wide mat with an average height of about 7 centimeters and a shell density of 234 shells per meter squared. Later in the experiment, we cut the mat so that we had an additional cross-shore width of 1 meter. We also looked at flat configurations of oyster shell bags. This image shows our 3-row configuration denoted by 3 individual oyster shell bags in the cross-shore. We looked at 1, 3, and 4 bag configurations spanning cross-shore widths of 0.5 meter to almost 2 meters. It's important to note that these oyster shell bags were almost twice as tall as the oyster mat. They were about 15 centimeters tall on average. and they used considerably more oyster shells in their footprints. Each bag contained about 210 shells. The hydrodynamics in this experiment were defined by a TMA wave spectrum. We used this spectrum to replicate conditions near shore in quiescent estuarine environments. And we had 3 wave periods, 1.5 seconds, 2 seconds, and 4 seconds. We had a total of 5 water depths from 8 centimeters to about 43 centimeters. For our lowest 2 water depths, we had a single wave height equal to approximately half of that water depth. And then for our remaining water depths, we had 2 wave heights, one equal to half that water depth and then one equal to a quarter. This resulted in a total of 24 unique hydrodynamic conditions with wave heights from about 4 centimeters to almost 11 centimeters and wavelengths from roughly 1 meter to 8 meters. To give an idea of what these conditions looked like, here is the lowest energy condition that we tested over the oyster mat. So in this video, waves are propagating from the upper right-hand corner down to the lower left over the mat. The water depth is about 8 centimeters, so it's in line with the crest of most of our oyster shells. Wave height was about 4 centimeters and the wavelength was about 1 meter. And you can see as the waves are propagating over the mat, their energy is being dissipated fairly well. Alternatively, if we look at one of our most energetic wave conditions, which is at a water depth of 43 centimeters and a wave height of almost 11 centimeters, with waves propagating in the same orientation as the video before, the oyster mat is in there, but it really doesn't appear as if it's having any effect on these waves. To actually quantify these effects, we looked at a wave transmission coefficient, which was calculated based on our incident wave height taken from wave gauge 9 and our transmitted wave height taken from wave gauge 6. This figure has a lot going on, so I'm going to walk through it step by step. It presents the wave transmission and reflection results for our oyster mats. The 2-meter oyster mat is represented in blue, and the 1-meter mat is represented in green. The triangles represent our greater wave height of the tested conditions. The top row of these figures is transmission coefficient, and the bottom is our reflection coefficient, with each column representing a different wave period, and each graph is representing water depth. So you can see from this figure that the 2-meter mat generally outperforms the 1-meter mat, especially at lower water depths, but these differences decay as water depth increases and the overall performance declines as water depth increases. Reflection is highest for the lowest water depth, which is to be expected, and then generally declines. And if we compare these results to our oyster shell bag data, where oyster shell bags of 1 row, 3 rows, and 4 rows are represented by pink, orange, and purple respectively, we can see that the oyster shell bags outperform the oyster mats across all of our tested conditions. There's minimal variation across the 1, 3, and 4 bags, especially as water depth increases. However, the 3 and 4 row configurations generally perform better. Reflection was also a larger factor for the oyster shell bags, with higher measured wave reflection coefficients for each of the configurations, but again, as water depth increases, those reflection coefficients drop. As I mentioned earlier in this presentation, the oyster shell bags were nearly twice the height of the oyster mat, so we decided to normalize our wave transmission coefficient results by the structure height. And we did this using the relative water depth, which is the ratio of water depth to the structure height. It looks like we didn't change too much, with the oyster mats still not performing as well as the oyster shell bags, but it is interesting to note that for increasing relative water depths, the oyster shell bags tend to maintain their performance, plateauing around the transmission coefficient of about 0.6 to 0.7. Interestingly, if we focus in on a relative water depth equal to 1, the oyster shell mat, the 2-meter mat, represented by the blue circle, outperforms all of the oyster shell bag configurations. This is very interesting because the footprint is roughly the same, but the oyster shell mat is using between 4 and 8 times fewer oyster shells than each of the oyster shell bag configurations. which suggests that the 2-meter oyster mat using less shells is a more efficient solution when situated in an appropriate hydrodynamic regime. We also looked at empirical formulas to describe the behavior of our oyster substrates in this experiment, and we considered existing empirical models in the literature that were referenced as being suitable for oyster-based living shorelines. The results for the oyster mat are shown in the top of that graph, and the oyster shell bags are in the bottom. And we have root mean square error for both substrates. For the oyster shell bags on the bottom, the formula of Shang et al., which is the blue square, had a very low root mean square error compared to the other models. For the oyster mat, the prediction behavior wasn't quite as good, but the Shang et al. Formula, despite the higher root mean square error, had a better fit of the overall behavior of the oyster mats. So we decided to move forward with the Shang et al. 2024 formula. That formula is shown in pink on this screen, and it is written in terms of a relative crest height and a relative crest width, as well as the breaker term, which includes the dependence on wave period. We took this model and refit the model coefficients to see if it would better describe our oyster shell bag data. And in this case, our wave conditions tested extended the range of submergences tested in the Shang et al. Formula, and we were able to get an agreement of about 85%. We tried to then apply this method to our oyster mat data, but the residuals on that data were non-random, suggesting that that model didn't provide the best fit overall. We developed a new empirical formula for the oyster mats, again dependent on relative crest height and including relative crest width, but instead of non-dimensionalizing by incident wave height, we used peak wavelength in order to include the effects of peak wave period. With this model, we were able to get about an R-squared of about 0.88, so describing about 88% of the variability in wave transmission with this model. And the root mean square errors for the original Shang et al. Formula compared to these two newer formulas show that we were able to reduce the overall error in predicting our wave transmission coefficients. This brings us to the conclusions for today. And number one is that the oyster shell bags outperformed the oyster mats across all common hydrodynamic conditions. Each configuration of those oyster shell bags performed better than either of the oyster mats. However, if we normalize those results by structure height and we look at relative water depth, and if we focus in on relative water depth approximately equal to 1, the 2-meter oyster mat performed much better. And this is, again, very interesting because it used far fewer oyster shells, and this suggests that the oyster mat, when situated in an appropriate hydrodynamic condition, provides a more shell-efficient restoration solution. And finally, we used empirical formulas to predict more than 85% of wave transmission over our oyster substrates. We tested existing empirical formulas and determined that the modified form of Shang et al. Was appropriate for submerged oyster shell bags, while the new formula is more appropriate for an oyster mat. And with that, that's the end of my presentation. I'm happy to take any questions, and if you want to know more, our paper just got published last week, so you're more than welcome to scan that QR code and check it out. And I'm gonna stop sharing so I can see you guys.
That was great, Delaney. I think you're definitely ready for ICCE. I will go get started with a couple submitted questions, but as always, if you have any that you'd like to ask Delaney now, go ahead and put them in the chat. I guess the first question, what are next steps in future work for the oyster mat structures?
This is a great question. There are a lot of things I want to do with this data. This is actually one of the first comprehensive hydrodynamic studies of an oyster mat. So my ideal next steps would be to test more cross-shore widths of these mats and then also look at varying shell density to kind of get at some of those roughness parameters and more oyster-specific parameters. I also think we need a field study because it would be interesting to see how these structures perform similar to oyster shell bags in terms of recruitment and then how they do in the field with wave attenuation. And I'm also looking at hopefully implementing them in some sort of numerical model.
Great. What challenges do you see with implementing the mats in the field?
I think the biggest challenge would be constructability. So, as I mentioned, we were able to build this entire mat in the wave flume, and Duncan Bryant graciously let us do that because a lot of our preliminary testing was us building these like quarter meter squared tiny tiles, but then when we go to move them into the flume, they would crumble. So, I think trying to build this as we did in this project isn't feasible in like the natural environment. And so we have to work on, I guess, how exactly you would construct this and maybe smaller tiles and different like base materials.
Have you defined a scope for future field experiments?
I have not. As I mentioned, I'd really like to look at oyster recruitment and then wave attenuation. And I think it's important to also look at wave attenuation specifically in different hydrodynamic conditions. So in my ideal world, we have a couple pilot locations for these to test with different conditions, sort of like that Morris et al. Study.
Did you consider bed friction model for the oyster mats?
We did consider a bed friction formula. Duncan actually suggested that, and we tested a couple, but the results that we got just didn't physically make sense. We fitted a roughness coefficient, and then when we tried to back that out relative to our oyster shell parameters, it just didn't make sense. So for the time being, I think the formula that we presented again represented 88% of the variability. I do think that future formulas should include more oyster specific parameters though.
Great. This this is another great question. Do you have a sense of how the oyster bags degrade over time, depending on material, and do they reflect any forms of that oyster mats create without human encouragement? Um, I guess really asking is like, what's the with the difference in material, what do you see the advantages of either the oyster bags or the reef mats, oyster mats?
I think the degradation of the oyster shell bag material depends on what material you're starting out with. So if you have some sort of like core material versus plastic, I think the core fiber is built to degrade quicker. And then I think the purpose with that is you hope that the bags at that point have accreted enough sediment in oyster shells so that they maintain that shape. And then I think they might reflect like a natural reef or mat shape. Um, yeah, I hope that answers that question.
Um, Thank you, Delaney. We can now move into general questions, and if there's any that I missed, we can cover those under the general questions that can go towards all of our speakers. Delaney, I have another question for you. Um, how did you consider, I guess, sediment um, interacting with the oyster mats versus the bags? Do you think that will lower roughness of?
I think that's a great question. I think there's kind of two components to consider. So first, I think the oyster mats are generally heavier per, let's say, quarter meter squared than the oyster shell bags. So there is potential for them to settle in a field study. And so we'd have increased sedimentation with that. And then the other thing is porosity. So the oyster shell bags in this experiment had a porosity, I think about 74%. In the oyster mats, when we measured porosity, it was about 90%. So I think there's definitely more space for sediment to accumulate on the oyster shell mats. and that could affect roughness, but also the health and growth and survival of the oysters.
Great. A question for Katie. For the Sea Hive implementation, what is just for general scale, what is the artificial footprint um of the seabed on the seabed?
Yeah, I was just reading that question. So the diameter of the ones that I was talking about are 3 feet. And so depending on the configuration, most of the time it's three on the bottom, two, and then one on top. So that would be probably about 9 to 10 feet wide. But if you wanted to space them, because sometimes, you might want something longer or something like that, there has to be 10 feet in between the installation of one configuration and then the other. So there would be spacing between them as well. Um, yeah. And then
Thank you.
I see the other one. Um, so as far as the conditions that I've been testing, they all are related to a site-specific set of conditions. I guess we haven't really tested. I've tested the maximum scaled like wave height, and that data just the probes that we have aren't like they basically were covering them with water, the wave probes that we have. So I wasn't able to test something of a larger wave height accurately, but the conditions are usually very calm because it is around South Florida. Yeah.
Just a little bit of kind of a follow on. I mean, and been some questions in the chat is saying, are these things designed site specific? Yes. Like at least for DARPA's Refence program, again, Katie was alluding to, South Florida has a much different wave climate than say Oahu. And so you see a lot of differences in the designs, whether you have, at least on the coral side, like, do you have a large reef crest structure and then smaller back reef structures? Or do you have maybe just two reef crest structures? And how far are those spaced apart? If there's alongshore gaps, which you'd want for circulation, like you wouldn't want manatees or whales to get trapped or something like that. You want some circulation. How wide those are spread apart is a function of incident wave period, things like that. So there's a lot of, you know, the Sea Hive's kind of a base design, and then again, when you go to deploy these features in the field, they're all going to be modified based on your water depths, your seabed composition, incident wave heights, periods.
Thank you. Another one for Delaney. Um, oh, I see you actually answered in the chat. Perfect. If anyone else has any questions, or
Tyler,
Delaney, if you see any.
yeah, we can do a general question.
Okay.
This one's open to everyone. We had a really cool webinar on remote sensing, and so one of the questions we got ahead of time was how different observational techniques like remote sensing can be used to test the efficacy of nature-based features.
Amanda, jump in. Looks like you're about to say something.
I was struggling with my unmute function, so that was just me playing around, and I did miss the question. But so you go first, and I'll use context clues.
Okay, well, was remote sensing applications for efficiency? Well, one of the efficiencies we want to look at is run-up reduction or erosion reduction. So things like Argus coastal monitoring stations are very applicable to that. Also, I mean, out of Argus systems, You can get some wave parameters. Obviously, coastal lidar systems are another thing. We're starting to deploy for trying to monitor not only the waves across the structures, but again, inshore, are you causing erosion, run up flooding? So yeah, there's a lot where remote sensing can be done.
Yeah, and we have a few teams that have been looking at inverse bathymetry using remote sensing and radar. Basically, it's like where you see the waves breaking is it's after Argus. Argus generated this research originally. That's where you're going to see that change in bathymetry. So a lot of folks are using that to monitor performance as well. And side note, this kind of tags on to like one of the questions about degradation, and Delaney was talking about how sediment plays a role in the reefs. I I just want to point out like some of the reefs and pilot projects we've seen, they have failed, and they've kind of the 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 feature itself has broken. And while if that was, like a seawall, we'd be like, well, that is now not an effective structure. What we've seen with those reefs and those case studies through things like remote sensing is that because of those failures, you get sediment interaction that actually ends up building up more, which we're assuming that means waves are breaking more. The wave power has less ability to move sediment, right? So it's actually kind of an interesting, as far as policy and O&M goes, an interesting role we have to play figuring out if that failure actually makes us have less erosion on the shoreline. Then how do we write that into the monitoring, and how do we write that into the O&M documents that say actually how do we create these pathways for that to be considered a success and possibly plan for that failure?
Amanda, I think that's a great point, and that's one thing we need to remember about nature-based solutions is, whether we put out a concrete base structure, we're having natural things, corals, oysters grow, and those do fail in nature. And so first and foremost, again, like, Amanda's, Erdek can build or design a bridge pier, and hey, that's supposed to stand the whatever 500-year storm. Well, during most tropical cyclones, these features do fail. And so one of the things in terms of design criteria, this is an important part of, the DARPA Refence program. They're like, oh, these features shouldn't, fail under a 100-year storm. And we're like, geez, a Cat 5 tropical cyclones, maybe a 25 to 35-year storm. So we can't have them being held to higher standards. But the thing is those features evolve through that process. You have a coral reef that gets smashed up and spread out, and now all those little pieces start to grow up. Or oyster reefs do the same thing. So again, both in terms of our consideration and design, but then acknowledging, I mean, that's the whole thing. Is you put a concrete structure out there, it's not going to grow. We want those corals, those oysters to grow with elevated sea levels and things like that. Or as the structure breaks, it regrows and fills in. That's exactly what we want. And that's a natural part of the process of these organisms. So that really needs to be accounted for in the permitting. The other thing is you were asking about the performance and remote sensing. One of the other important things I just want to point out with remote sensing is also, again, we're not just looking at a static structure. We want oysters to accrete and grow more and more, corals to grow more and more. So remote sensing is extremely important for evaluating the development of that ecosystem, to go back and remap, has it grown vertically, has it increased in roughness and things like that. So remote sensing, optical, acoustic, things like that are very important for evaluating that part of the performance of the organisms on the base structure.
I have another question for general audience. I guess this includes me too, but what sort of research gaps do you think we see in doing this kind of reef-based research? Kurt, you can go. I feel like you have thoughts.
Well, right now, N is like one or two. Again, not knocking. I mean, beaches are very difficult, but you have a typical Dean profile. Oyster reefs, coral reefs are so many different shapes and sizes and things in the real world. And we just need more field studies to show their performance. I mean, we can do things in the lab, but how do they really perform out there? This is one thing on the what used to be this Coastal Engineering Research Board or whatever that was, is that was one of the things that came up at the 100th meeting is we need more samples because there's such a broad range in nature out there. So that again, you know, the idea of roughness and bathymetry and those try to determine friction factors and things like that. There's a lot to be done there. Also, porous structures. Again, these are porous structures. We usually think of like a solid breakwater or something, and as your mesh bag, your oyster bags are showing are these concrete base structures. Those void spaces, again, how do we incorporate those in larger scale coastal engineering models? Because that's a subgrid cell process. Are we doing it just as an energy sink? Are we modifying things like sub canopy kind of features or vegetation modules or some of the ways we're trying to play with like say X beat, try to get pore structures into something like X beach or swash. Like, can we kind of tweak it and goof it? But again, there's so much variability out there. So, taking like those open foam kind of simulations where we're modeling things at the scale of a centimeter and trying to use that to guide how we're doing a 2 meter cell in a larger coastal engineering model that we have to use to assess coastal flooding performance or coastal erosion performance. So there's some thoughts.
Yeah, super agree with those, especially when it comes to the life cycle analysis part. I think we can do the roughness bathymetry change in a numerical model, but like a G2 CRM or XBeach is not gonna like that whole like builds itself back up part doesn't that doesn't happen in any of our models. We're not capturing the geomorphology change. Once it failed, it failed. I think also something I think is a gap in knowledge is, as a callback to like the natural infrastructure, multiple lines of defense. I've seen a few studies look at this, but maybe like three is how many mats do you put, or how many of these sea hives do you put in a row, in 3 rows? At what point are you getting no more return on benefit for adding the feature? At what point are you maybe creating higher waves? I think that there's a lot of like you just think more would be better, but I think of the 1 or 2 studies I've seen, there have been less return on benefit for more features. And I think spacing, like you mentioned, porosity, all play into that as well. So more studies, more answers. And then, sorry, last one. I think as an engineer, we see this like kind of also what Kurt says, like it's a submerged breakwater, right? So it's just based on the depth is where we would put it for maximum benefit and wave reduction. That does not align with maximum growth maturity where the spat wants to go. So I think more joined research between the ecologist and the engineer needs to happen. So that was my last one.
Great point.
It's tough to go after you guys. You hit all the things I was gonna say. I think I guess I can get super specific, but when I've tried to parameterize these features in XBeach, there's a couple of different ways to do it, but I feel like so far I've not been successful. We can use like a Manning's roughness coefficient or porosity, and then as Amanda was saying, XBeach doesn't let you have multiple elevation values per grid cell, so you can't get like the concavity of an oyster shell, or if it's growing out and then back up, it's just really difficult to make that happen. I have seen some like I think it's a different modeling software, but it's super expensive, not open source. They're able to take like a 3D scan and then put that in their wave flume. So I think it would be cool if we could get more developed technology that allows us to do that while still keeping it affordable. And then, as Amanda was saying, I think we definitely need more field studies for oysters specifically on ecology and growth and recruitment, and then also making sure, like, balancing the engineering goals with the ecology goals. Katie, did you have anything you wanted to add?
Yeah, I was gonna say in terms of parameters, all the literature is most of the time empirical. analysis done in the tank. So the reflection coefficient transmission of a specific geometry of someone's new design of a submerged breakwater really has to do with whatever they built in the tank. And that is hard to see where they get some of these constants and numbers. So you kind of have to trace back in the methods to see that. So that is, not everyone has a tank. Not everyone can do something like that, which is hard to implement, or to model something that they don't want to immediately put into the water. And we've seen that before as well with nature-based solutions like the Sea Hive. Once it's in there, you can't take it out. There's going to be things growing on it, and it's going to be established as a habitat. So we have to make sure that it's already, or we've done enough testing before it actually goes in the water. And the other thing that was being talked about before, I had someone from the like the coral lab come over and ask me some questions a couple days ago. And I think during my experiments, he's going to come in and kind of just like while I have my structures in the tank, look at some of the questions he was asking me. So one of them was, how do they affect each other? So how does the coral growth and settling around the structure impact the dissipation and where they would choose to settle and things like that? Where the highest energy exists around the structure and whether or not the animals and the corals would be impacted by that. And as well as how does the shape of the Sea Hive impact the corals and other animals that would choose to live around there. And so I think that's just such a deep question that is kind of hard to answer because they go, they are so connected with each other. But the more collaboration that we have with them, the better.
Kurt, did you want to add anything to that?
No. I think great point. I guess one other group I'd say we probably have to drag in a little more on this is the socioeconomics folks, because we're not just like, hey, a bulkhead, and we know a cost of that, and we can do a hazard risk reduction cost. But now all of a sudden we're talking about working with ecosystems that have recreational, commercial fisheries, and these other values. So again, if you have to run a cost benefit analysis and try to look at return on investments, I wouldn't say we're scraping the surface, but we're missing a lot of those bigger ecosystem benefits that would allow for, again, these larger sums of these pre-disaster mitigation funds, post-disaster recovery funds. If we could incorporate some of those other ecosystem benefit in those cost benefit analysis, it'd make these even more attractive. And again, then you're really starting to talk about boosting the economy, fisheries, tourism, those things. So I think that's important. One thing I will have to say, because we just held a session at Ocean Sciences on this topic of reefs and coastal. Katie was there. One thing I think we should think about is just because Katie, you and Delaney showed in your presentations, was just KT is a wave transmission, which is just purely wave height. We know, at least on coral reefs, and sorry, it's a lot hard to think about like, 10 centimeter high waves at 2 seconds. But when you have wave groups, you have bigger waves break further away from the structure, smaller waves break close to the structure. And so you're having an infragravity wave paddle. And so one of the things is we see wave propagation, breaking on reefs or propagation over reefs, is transformation to lower frequencies is a big thing in coral reef environments. And so if we're taking a metric, just KT, and we're not taking into account that period in there, so I would strongly suggest we start thinking about using energy flux as a more important metric. Because again, you might create a large loss of wave height, but if you're pumping into very much longer periods, those periods dominate run-up, dominate coastal erosion processes. So not saying that KT is not important, but you're not getting the full story in terms of what that means in terms of coastal impacts. So just a quick thought. I'll get off my soapbox there. So.
No, I think that's a really cool point. I think looking at energy flux would be something that if I got to do another physical modeling experiment, I'd have more sensors and consider that a little bit more strongly. We have about 10 more minutes left in this webinar. So if you have questions for any of our speakers or just like general discussion topics, feel free to drop those in the chat. I can give us a softball question. For our four speakers, do you have a preferred methodology between fieldwork, numerical modeling, or physical modeling?
I think they all have their place in being. I am a numerical modeler. Obviously, I love numerical modeling. If I could go out in the field all the time, though, I would do that. So that's the coolest. Yeah, and then you guys are doing the physical. I think it's really important just because you are really great at holding a hammer that not every answer that's a nail. The numerical models, they do a great job of getting geospatial temporal variation that maybe you can't get at your case study. I think the case study helps you understand how these different interactions between the finite and the big scale, the medio scale stuff I talked about, you see how that interacts at your site with seasonal variation if you can get it for more than a few months, with that real life scenario, that undefined variable that you didn't realize should be in your system. And then I think physical modeling helps us do both of the other two things, like create the system that's going to be a good pilot test before you have a failure in real life. You can do it in the flume. And then obviously all of the data, the coefficients of drag that we're putting into our numerical models, they have to come from somewhere. And a lot of it's empirical, but I think the most unbiased data is coming from our flumes. So I think they have a nice ecosystem between the three of them. And obviously, I'd rather be out on a boat every day. So, but I think they all have their place.
Yeah.
I think that's a
Life's
great
better in
answer.
flip-flops, right? But the thing is, going back to it, and I'm a geologist and oceanographer, but an engineer, you're going to design something to meet some threshold criteria, the 20-year, the 100-year, something like that. And unless you just are the luckiest son of a gun, you're probably not going to get those conditions during your field study. And so we need to do that. Plus, the other thing is, again, if we're going to try to take it and get like these hazard risk reduction funds, like you're going to have to model the resulting impact of a structure that doesn't exist yet, to say, okay, well, gosh, we're going to protect X number of lives and dollars to feed a benefit cost analysis, and then okay, then we can finally get it out in the water and measure it. So we're always going to need that combination. So I love what Amanda said, that we need all three parts of it.
Katie, what are your thoughts?
It just made me think about how there's so many flumes in the world. Even at Ocean Sciences in Scotland, it was like, oh, this country and this university has one, and it was funny to see, but I felt a bit obsolete when I first started working in the tank because of the numerical modeling. But every time I've said that to anybody, they said, no, 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 we need you. And it is important to have that because all the constraints come from what we can model in the tank. So I guess I like it. It's slow, just like everything else. You expect a sensor to work and then it doesn't, and then you're back to square one a little bit. But it's all part of, the process of science, I guess, which is pretty slow. So I do enjoy the physical modeling aspect. Um, and it's cool to be able to see something like that house that I showed. No one's going to be able to get a bird's eye view of, of the winds over that. So.
I'm kind of in the same boat. I agree with what Amanda said, and I feel like I enjoy those three methodologies for answering specific questions. But if I had to pick my favorite, I'm definitely very big into the hands-on approaches. So physical modeling and fieldwork are my favorite things to do. And I'd like to kind of backpack off this question a little bit, and this question's more for Amanda and Kurt, but do you think that future funding of research, do you think there will be more emphasis on numerical studies because they're generally less costly than a major field study or a physical modeling study?
Everyone wants to go into the field. Let's be honest. But and this is again we talked about it on the board for coastal engineering research is that I think it's very important, for both Amanda and I as federal government, is we need to publish that data so they can be used by others. Usually it was like, you know, when I first came out, Scripps would do this study and Scripps held that data as their own or Oregon State or something like that. At least the federal government now we're required to publish that data. And that's good because again, you could come in and if you look at places like NSF, like, oh, we want $3 million to conduct a big field experiment, do modeling or you want $200,000, we're going to use existing data. You know who's going to get funded more frequently is that. So I think it's important, but I really think it depends on us for the publication of that data, making it publicly available. For us in the USGS, every time we put out a sensor, if we publish it online. So if you're interested in coral reefs, you can go to the USGS Coral Reef Wave and Water Level Database. So we have full time series from all of our sensors. So if you want to process it looking for infragravity waves or VLFs, that's you can do it your way versus our way. That's important. The nation, the public, you pay taxes. That's your data. It shouldn't be something that, oh, I got my proposal and I'm height, it's for me only. I think that data should be made available for others so that, again, then can be used for modeling. Because one of the big things is we're always like, oh, I have my data set from my field experiment. Delaney, what you did is you took someone else's and you showed how yours fit there. What you want is data across multiple field experiments to develop really robust empirical solutions.
Yeah, I like that point, and I mean all of our data needs to go to the same data depot so that we can pull from it, streamline, standardize practices. I think that to answer your question about like maybe federal funding going towards numerical modeling versus physical, I think we've been seeing that for a long time. Actually, there used to be an entire replica of the Mississippi River that we carved out of concrete to represent coefficient of friction. Now we have new technologies, but I think, yes, there with the GPU becoming a thing, resources becoming, and I'm talking like 10 years out, resources being cheaper, we will see that. And then pause, but that'll be for existing conditions. As we see more companies, more industry entering the space of innovative designs around NBS, we're having a lot of tools that we've never seen in the field before. And I think we're going to replace as is conditions in physical modeling with testing those tools, doing like what you guys did, CHIVE, and seeing how they have an impact in hydrodynamics. And we can only do that in a physical model because we can't risk communities seeing them not work. And I'm going to piggyback my question to you guys and saying, since you have had experience in the physical model, Katie, Delaney, for both of your projects, what do you see? What's next? What needs to be done based on the findings you saw?
Katie, do you want me to go first or do you want to go?
You can go.
Okay. Tyler asked about, I think, my future work, and I think for the oyster mats specifically, I think that it would be really interesting to look at the effects of specific oyster parameters, like shell sizing, or median shell size, shell density, and then there's also different types of oyster reefs. So I feel like these mats could potentially be used as like a proxy for what our natural reefs are doing in the field, and we would need more testing and more data to see if that's possible. So I just think we need more testing personally, and I think probably more field studies to see how these work in nature, and then maybe coming back to physical modeling if we want to look at other questions, and then we can expand into numerical modeling. Katie, do you want to add?
I would agree with looking at implementing the sensors and the sites that we have and looking at that data as well. It's kind of hard to do that because when we have wave probes in a tank, we have 16, for example, like there you can't really put 16 sensors out offshore and inshore around the structure like that. So you're limited in that way. But it would still be good to compare that data. We have wind capabilities, like I mentioned, and I think trying to do that over a structure, that's not very common in the literature to look at shallow water wind generated waves. And so we're looking into that as well as irregular waves, which I have run a couple times, but I need to do more with those because regular waves are kind of the baseline when you're running tests in a tank, and they're easier to look at least in the beginning. So I will be doing that as well. We've looked at a lot of different configurations of them, except for the sea hives backing a seawall. So I think that would be interesting in the tank as well to look at. You have this concrete seawall, how much is it reflecting? Probably close to 100%. When we start putting the sea hives up in that stepped configuration, how much is it reducing that reflection? So,
Amanda, I hope that answered your question. That brings us to 3 o'clock, and so with that, our webinar has come to its conclusion, and I have a conclusion slide. There. Okay. So I just wanted to say thank you to our speakers. It was awesome having you guys here. I think S&P in general, this was a really cool topic for us to touch on. And then me personally, I love reef-based research. So I appreciate your time in coming today. For our audience, if you have any questions, you can reach out to each of our speakers at their emails. And for those of you who were requesting professional development hours, please reach out to Annie Mercer by 5 p.m. on Friday to get those hours. Please note that full attendance was required, so you will not get hours unless you were here for the full webinar. So yeah, thank you everyone. And if our speakers want to say anything else, feel free. Otherwise, thank you very much.
Well, first off, Katie and Delaney, great presentations. And also Delaney, Annie, and Tyler, thank you for hosting us. We greatly appreciate it.
Yeah, this was
thank
great.
you guys too.
Thank you
great.
guys.